and delta T for the hot shot. Great. So all we have to do is know the masses and the temperatures. Might as well express the temperatures first. It was pretty obvious that I measure the initial temperature of the hot water in a shot, I measured the initial temperature of the calorimeter cup, then I measured the final temperature. So those three temperatures, which I will call temperature hot, temperature cool, temperature final, they equal something. I don't know what they equal, but that will equal something. Of course, delta T hot shot equals delta T hot water equals T hot minus T final. And of course, delta T calorimeter cup equals delta T cool water equals T final minus T cold. That part's easy. Now we have to start thinking about the masses. It's not going to be too difficult. Who's close? Maybe you could grab that balance right above your head there. Anytime you need any of that equipment, you're certainly welcome to grab it. Thank you so much.
Wait, Professor?
Yes?
Isn't the delta T hot water supposed to be T final minus T hot? Because
Thank you for asking. I wondered if anybody could. Let me start by going back to the initial statement. Is it clear from here that everything is expected to be positive? This is what's losing heat, that's a positive value. This is what's gaining heat, this is a positive value.
Yeah.
Hence, therefore, the delta T's must be positive. All it's asking is the temperature difference, not what direction you go.
But see, when you bring it over though, and you minus it, that was the, if you take T
This
final
one?
minus, yeah.
That's an algebraic minus, that's not a physical.
Yeah, I know. So you need the minus.
This delta T still has to be positive because this one means you subtracted from the other side. So it's an algebraic negative. That delta T still must be positive. Don't confuse negative and positive signs between physical reasons and algebraic reasons. There are physical reasons for signs and there are algebraic reasons for signs. And both apply. Without getting down here, not worrying about algebra, you just say to yourself, all of these delta T's are expected to be positive. Don't even think about this for a minute. So you have to, all they're asking here is how much did the temperature change. It doesn't care which way it goes. In fact, by calling it heat loss, it already knows that this delta T is a loss in temperature. Calling this a heat gain, this is a gain in temperature. I therefore make them positive for physical reasons. And then later, when I do the algebra, that's a whole different issue. Oh, okay. It'll be easy to determine the mass of the shot. Let me, now the experiment is over, I'll get rid of the water as best I can. Put the shot here. And I'm going to give it a few minutes to dry off. Because, you know, the term that says hot shot is only shot. It's not anything else. So I'm going to give it a minute to dry off. It doesn't take much. I find typically that you give it just a minute on a wet towel like that, and you put it over here on a dry towel. And if you do it while it's hot, it dries out real quick. So, do a third one here, and then it'll be all done. But be careful not to lose any of my shot, please. Okay. So while you're writing your data table, you get that kind of spread out like that, and it's drying off. When it's finally dry, you can gather about. I'm being hasty here because of time. I think I would put it up. I'm going to do it one more time just to be a little more careful about what's going on here. No, look at that, the table is wet. It's always nice, we end up with clean tables after this experiment. Anyway, if it turns dry this time, great. If it doesn't, we're going to pretend like it's dry. There's all the shot on there. That's pretty dry. So now I can take this over and determine the mass of the shot. So if it wasn't exactly, let's see. Ah, perfect, 60 grams. Well, I got the mass of the shot. Now, when we started, I just did something I asked you not to do, and that is don't lose my shot. At least I know where it is. We started with hot water and hot shot together. How much water? You don't really know. The reason you don't know is because all the time it's boiling, it's losing water. So I'm going to make a suggestion here. That is, determine the mass of the cup. Oh, look at that. It's a perfect 50 grams. Okay? Then put the water in it. Do it one more time for me, please. Just like you did last night. It's perfect. Then put the water in it. He's so careful. Now you get the mass of the water plus cup. Oh, look at that. It's 90 grams. Perfect. Okay. So I now know how much water is in here. Do the experiment. Now you can determine the mass of everything. Oh, look at that. 150 grams perfect. Okay. So we have measured, let's see if we covered everything. We can figure out how to get the mass of the shot. We can get the mass of the calorimeter cup. We can get the mass of the calorimeter cup plus the cool water. And we can get the mass of everything, which is shot plus calorimeter cup plus cool water plus hot water. Do you see here, with subtractions, we can get everything we need. Mass of shot, mass of calorimeter cup. Here is the mass of the cool water by subtracting these two. And then by subtracting 1, 2, and the third one, we can get the mass of the hot water. So we can get all the masses through these measurements. Yes?
Is the cup made of aluminum?
Yes. Yes. What's the specific heat of the cup? And it is aluminum, and it states a specific heat out here, but you'll notice that there are no units on this one. That's because it's actually in calories, and we probably should calculate it in joules. So don't use this specific heat for aluminum. Just say the cup is aluminum, so states on the outside. It says aluminum on the outside. And the aluminum, the specific heat for aluminum from the text will is. Don't use this value because it's using a different set of units.
So we're going to have to look up the specific heat.
Say it again?
You're going to want to look up the specific heat.
Yeah, look up the specific heat of aluminum and water and all the stuff you need. Between now and 2 o'clock, between now and lab time, I'd like you guys to design a data table that, number 1, records raw data, and then number 2, makes it convenient to write whatever calculations are necessary. In this case, I mean subtractions. And then at the very bottom, do the calculation for specific heat. If you have a really good data table, I would like you to use yours. If you don't, I'll write one on the board if you want to use it. But I'd really rather you make up your own data table, because you're the ones doing calculations from the data table, so lay the data out in a way that makes sense to you, instead of doing it the way it makes sense to me. But like I say, if you can't come up with one, I'll certainly make a suggestion. Okay, so, probably for this time and this time only, I'll tell you the purpose of this experiment, of course, is to determine the specific heat of an unknown metal. And I think only at the very end will you admit that you are suspicious that the metal is aluminum, and you can finally compare your answer to the specific heat of aluminum, but only in the conclusion section. I'm suspicious that I have aluminum because I have this value and the specific heat of aluminum fits within my tolerance. Or, I thought I had aluminum, here is my experimental number, and it's quite different than the real aluminum number. So either it's not aluminum, or I need to improve my technique. Yes, I should mention this one last thing about Physics 6 experiments. And it starts with an old joke, maybe you've heard it. About the two students walking down the hall. One student says to the other, "Oh, how are your classes going?" So, "Well, I guess everything's fine, but I'm taking so many lab classes, I just don't even know what lab I'm in anymore." First student says, "Oh, it's easy. If you're in lab and it smells real bad, you're in chemistry. If you're in class and your experiment is green or it wiggles, you're in biology. But if you're in class and your experiment doesn't work, you're in physics." Well, it's true, and part of the reason, chemistry, some of those experiments can be dangerous. Biology, same thing. So in those experiments, very often, the lab teacher sets everything up and makes it almost cookbook. Do this, be very careful here, make this measurement, set this down over there. In physics, it's really hard to hurt yourself, but if you try. So typically, we don't set it up so well for you. What we do is we get a rough experiment. It's your task to try to make it as good as possible. And we don't grade you on whether or not you got the correct number. We grade you on whether or not you stated what you were trying to get accurately. You did the best job you could, and then you know whether or not you accomplished. That's the key issue right there. If you accomplished it, you so state. If you did not accomplish your mission, you so state. That's all it takes to get a good grade. You don't have to be right. You have to know whether or not you are right. That's all. So in conclusion, if you decide that you want to say, if you want to admit that you knew it was aluminum, then you can say either my number is really close, the correct value for aluminum is within my tolerances, therefore I think the experiment went well, or I got this tolerance on my experimental number, here's the real number for aluminum, and they differ so much, I need to refine my technique. And you might suggest some things that would help to refine your technique. Any other questions? Yes?
Will your standard deviation all in there, and you need to do multiple experiments?
You need to do multiple experiments to have a Gaussian curve and a standard deviation. In this case, I don't think we're going to have time to do multiple experiments. You're only going to have time to do one. So we won't be doing an average value and a standard deviation. We'll just be doing one value with a tolerance on that one value. Yes?
Because of that 2-to-1 ratio for hours and credits you mentioned, would that mean that the experiment should take more than an hour?
It shouldn't take more than an hour to actually do the experiment.
And then we finish the write-up before?
Finish the write-up during the next 2 hours.
Okay.
Or quicker if you want to leave it. That's one of the reasons why having it set up ahead of time, the purpose statement, the data table set up, all that stuff set up ahead of time, you can get done well within the 3 hours.
So it's like a handwritten write-up?
Yes, absolutely. Yes.
So because we're doing it Mondays now and the lab write-up is due at the end of class,
Yes.
it's handwritten.
Yep. And I grade you, ladies and gentlemen, full credit is on 3 hours of work. If I see what looks like 3 hours of good work, that's full credit in my opinion.